Yesterday the hanging column method was shown in the laboratory. Hanging column method or negative column method. Although the setup appeared to be slightly different, but it is a wonderful method to evaluate the suction values at low suction values, especially good for sands or something else. So what is the principle behind this? For example, if you have a funnel or something, a container which contains soil in it, right? On the right hand side there is a soil, and if it is connected to a water reservoir, so there is a water reservoir that is connected to the soil. It could be a column or it could be a small container containing soil. Now water is in direct contact with the soil, so what is expected? Water would raise to this level, right? If this is connected, soil is connected directly with water, and you expect that the water level would be here, correct? So soil will be completely saturated. What if I raise this part? What is expected? And what if we leave this particular part, if it is hanging? Would the water dip and soil will become fully dry? If you are raising continuously, then what happens? So the level would be here, but it would go somewhere here, right? If this is taken to here, then what will happen? The level is only here, water level is only here. So would there be any water here? In fact, fully water will be present. If the soil is, if soil air entry value is more than this particular head difference what you are seeing, then definitely water will be there. There will not be any discontinuity. So this water will be available against the gravity. That is what, no, if you take clay soil, fully saturated, water will not dip out. You take from consolidation, after consolidation, soil is fully saturated. You take out the soil, hold it, water will not dip out. It happens in sand because sand, the suction or soil water potential is less than the gravity force, right? Finer and finer, it will be able to hold the water. That is the tension we are talking about, right? So that is a method what we are trying to use in hanging column method. So therefore, a large column with compacted with sand or any soil which is compacted and connect to a reservoir. This is a reservoir. This is a reservoir. This is a sand column. Now water is expected to be up to here, wherever the water level in the reservoir. Above this, you may have some capillary, and after that the water current would be decreasing. So at any distance from this level, this particular level, say if it is 1 meter, a 10 kilopascal suction would be there. I can measure the water content correspondingly, correct? Above the water level, that is a negative pressure only within the soil, correct? So that way I can establish the soil water characteristic of simply for sandy soils using hanging column method or negative column method, correct? So but this is suitable only for such soils because by 2 meters if you have a column, that itself is difficult. So that means within 20 kilopascal entire SWC should be established, correct? If it is 20, should have this. If 20 is somewhere here, then it is not useful because you will have only these points. Right? So in sandy soils, as the air entry value is nearly around 2 kilopascal or so, this will be useful, very useful method to evaluate the SWCC in the laboratory. Okay. So generally we placed volumetric water content sensors, like what I showed in the morning. So those sensors, based on resistivity and other things, they work, and generally they are related to dielectric constant. So dielectric constant of the media. For water, the dielectric constant is 80.4. For air, it's 1. So in between, partially saturated, based on the dielectric constant, it directly gives you the reading of volumetric water content. So that's the concept we use. So based on those sensors we'll place at different points. Now we can raise or decrease this level, so that we established hysteresis, a drying, wetting behavior for several soils, coarse soils, right? This will be a good method to establish that. Tensiometer, yesterday also there were a lot of questions. Tensiometer, very old method. In soil science, this has been used in since time immemorial, because for the crop growth, etc., people measure suction values. The suction should be less than the wilting point, otherwise plants die. So the tensiometer, amazingly, it works with a principle called using the concept of air entry value. So you have a higher entry disc. This is something like a higher entry ceramic disc. So it's just like a porous stone, but it has a finer pores than your porous stone. Porous stone, which you use it for the odometer or consolimeters. So it's finer than that. How fine it could be? It can be as fine as 1.7 into 10 power minus 3 mm. That will give a air entry value of 1 bar. 1 bar is 100 kilopascal. Imagine if you want to go for 15 bar, 1500 kilopascal. The size should be in the range of 10 power minus 4 mm. Very fine. Beyond that, we can't reduce. As some Bhargav was asking in the previous class, can we design something, small pipes, etc. This itself is very tough. But soils have much higher suction or thinner pores, finer pores than the ceramic disc what we can design. Maximum capacity is 15 bar. That's it. Beyond that, I haven't seen. Commercially available air entry discs, maximum capacity is 15 bar, 1500 kilopascal. Right? So essentially it has pores. Pore size is defined, very well defined. Uniform pores it has. Now if this disc is placed here at the sensor tip for the tensiometer, and this is fully saturated, because this entire column is fully saturated, right? You need to saturate the tensiometer before placing it for the measurement. This is fully saturated and disc is here. If it gets fully saturated, this side, this is a water column. This is water column. This is soil. So in between, what you have is ceramic disc with tiny pores. Pores are filled with water. Now this is acting as an interface between soil and water reservoir. So what is expected? Here the potential is low. Here potential is 0. What is expected? Water should move out. Correct? Water should move out. But if I tightly close this reservoir, water reservoir, can the water go out? Water can't go out unless until this is replaced by air. Correct? It has to be replaced by air. Then air has to come from soil only, because there is no other way. From only air there is a passage. But whether this ceramic disc could allow air to enter, it depends on the air entry value of the ceramic disc. If the pore size is 10 power minus 1.7 into 10 power minus 3 mm, which exerts a 100 bar, which has an air entry value of 1 bar, which is 100 kilopascal. If the soil has a suction of 80 kilopascal, right? So air cannot enter. Air is restricted. Then what it does? It tries to exert pressure for taking the water. So this negative pressure is transmitted to the water column. That is measured in a gauge, which is given as 80 kilopascal. That is how tensiometer works. So clear, right? Water cannot come out. but air cannot enter. That is the situation you are creating. So therefore the negative pressure is transmitted to the water column, right? It is in tension. Just like a capillary is placed in a reservoir, there is a negative, water raises, completely saturated, but there is negative pressure. Exactly the same situation you are creating here, right? So, but it has some limitations. Limitation is, this is something, this is very old type. If you try to purchase in market here, local market, for even 5,000, 2,000, 3,000 also you get tensiometers. Old type, which has a pressure gauge, etc. Which will not last for long. Now you have digitized ones. Digitized readings you will get directly, TA tensiometers, etc. This is what we are trying to use. And directly the data can be collected, which can be connected to data logger and which saves the data. You can also set the interval so that it can save the data for you, how often you want to record, right? So which has certain limitation. Limitation is not coming from the air entry ceramic disc. Disc I can improve to 15 bar, like 1500 kilopascal, but it can't measure beyond 100 kilopascal. Okay, so limitation is coming from here. So this porous ceramic disc, when the soil suction is say 1500 kilopascal, when I just try to place it, what is expected? The negative pressure is transmitted to the water column, right? So if the soil has a negative pressure of say 150 kilopascal, what does it mean? With respect to atmospheric pressure 101.325 kilopascal, around 40-50 kilopascal is less in the water. So we have concept of vapor pressure we heard in the previous class yesterday maybe. So if the vapor pressure is falling below the saturated vapor pressure, cavitation takes place. Cavities form here. Bubbles will form. So we saw the phase diagram, right? Yeah. We have a phase diagram, right? So here, at the same temperature, either by increasing the temperature, you can change the phase from water to vapor, or by reducing the pressure. At the same temperature, if you decrease the pressure of the water, phase transfer will take place. If it comes down below the vapor pressure, around 3.515 or something, what we estimated yesterday, at room temperature, if it comes below that, cavitation takes place. The same phenomena what we experience in triaxial systems, saturated triaxial systems, when they are heavily compacted, when you are doing a undrained test, this happens. Okay, if the back pressure is low, then this can happen. Okay, because if you remember, it has a tendency to expand if it is a drain test. In undrained test, it can't expand, but pressure drops. It goes to negative, right? This is shear strain, this one. You remember this kind of a curve? It goes to negative. If this negative value is large, then cavitation takes place. That's why you need to increase the back pressure. Higher back pressure, you need to conduct the test in CU. Okay? Same thing happens. So this has a limitation that it can't detect or measure the suction values beyond 100 kilopascal minus vapor pressure. Okay? So this is 100 kilopascal or 101.325 in Guwahati. If you are measuring in somewhere in Arunachal Pradesh up, what will happen? Atmospheric pressure itself drops to 80 or something. Your measuring range also drops. So then you can only measure maximum value up to 75 or something. Beyond that you can't measure. Right? So we have done a lot of tests. Not just that. Even for sands, even for sandy soils, if you use tensiometer, the equilibration that is required to establish the negative pressure within this water column is large. So forget about clays, silts, etc. This is a Brahmaputra sand, and either one is just simply, taken a soil in a cover polythene bag and then place the tensiometer, and then we were trying to measure readings. Second, in a compacted state, we were doing this. You see, for certain conditions, it takes even 2 days to get one reading. Equilibration time is very large. This is for Brahmaputra sand, almost like a uniform sand, uniform fine sand. So imagine what happens with silts or something else. So you cannot get an instantaneous reading using this particular method. So the difference which comes is this: for the drying and wetting path, this is the equilibrium values. We waited for nearly, the test itself was conducted for one drying path nearly 30 days or so, more than that. And this is what we got, and this is for instantaneous method. What you want to do? Just put the soil and connect with the reservoir, just let it pond, and connect one tensiometer, another water content sensor. Instantaneously it starts giving reading, That's what many are doing. It's not correct. So therefore, I don't recommend to use suction sensors in the field. You should establish SWCs in the laboratory for a representative soil sample, then measure the water content. Water content, it's a very quick method. Immediately it gives the reading. The variability associated with the atmospheric conditions, the soil variation, soil moisture variations, very quick. Within that, the suction sensors cannot, detect the values, right? So if you are thinking that, okay, I'll put a one tensiometer in the landslide or slopes, it's not possible, right? It doesn't give a correct result, because continuously water contents will be changing. Night will be different, morning will be different. Within the daytime itself, the variability might be there. RH, temperature, water content, etc. Rainfall, etc. There is a wonderful method. These are all very old methods derived in soil science. Nothing to do with geotechnical engineering. Geotechnical engineering, we've been using conservative designs, and in soil science, they came up with amazing techniques. Okay. This is a simply same HAE disk. What we saw that when the water column negative pressure becomes more than 100 or so, then the vapor, cavities are developing, right? So what they have done? Okay, I'll do something. Suction is what? UA minus UW, right? So if UA is constant, that is what is the problem, right? UA is 101.325. At mean sea level. If this is increasing, again it is coming down. So what if I increase this fellow? That's the concept. Axis translation is, instead of controlling the UW or something, you control UA. So they connect to like a cylinder or something. We have cylinders, right? At home we use cylinders. Just like that, they connect. They increase the air pressure here. So that's it. When you are increasing the air pressure here, and UW you can control or keep it at 0. Now you are changing UA minus UW. Suction itself is getting changed. So problem is with the atmospheric pressure, right? If atmospheric pressure is elevated, then there is no problem. So that is a concept in axis translation technique, but it's I should say, very, very time consuming, highly time consuming.
3 months.
Sorry?
3 months per cent.
More than that it takes. Very difficult actually. So advantage is that this method is used for when establishing hydraulic conductivity function. Theoretically it is possible. Theoretically you can establish hydraulic conductivity function, HCF, K versus psi, or water content. Same method. Okay? Outflow technique or something they call it. It's exactly the same method, same equipment, but very, very time consuming and very difficult to do that. I think you would have seen the osmotic technique. A membrane, semi-permeable membrane, and you have this is a PEG solution, polyethylene glycol, and the molecules have certain size where I can control the size of the molecules. Also, I can control the pores of the membrane, right? So I don't allow the PEG molecules to enter to my the membrane. So within a membrane, I confine soil samples. Now, what is expected if the soil is wet, right? Initially fully saturated. Water is expected to come out because PEG molecules are not able to enter. So the PEG solution concentration comes down. I can measure those concentrations. Yesterday would have seen Brix index or something, right? Light reflectometry. Using that, I can measure the concentrations. Using that, I can detect how much is the reduction in the concentration, what is the suction. Because the equilibrium or chemical potential of this one is known. Based on the chemical potential, I can measure what is the suction inside. Because suction here and outside, it should be same. Potential should be same, right? For both at equilibrium. So that's what I do. Even we have done for compacted soils. By varying different membranes, by varying different PEG solutions, we have done a lot of tests. In fact, my first student worked on this. Several compacted bentonite samples. This one also might have been demonstrated yesterday. Dew point potentiometer, which exactly works on measurement of dew point, relative humidity and temperature, right? So essentially, if you take a soil sample and then bring it here, it tries to evaluate what is the vapor pressure, right? So what it does, if the soil sample has certain UV, it tries to cool down wherever the formation of dew takes place. So that is the point dew has formed, right? So initial temperature was known, so it can evaluate UV. If UV is UV is known, you can understand what is the RH. If RH is known, because at what temperature the UV sat is known, right? In a given temperature, the corresponding UV sat is known. UV by UV sat itself is RH. If RH is known, temperature is known. Using the Kelvin's equation, you can evaluate. From the Kelvin's equation, you can evaluate suction, right? So this is the method it uses, but I don't have slides, but for a higher RH, 99.99, 99.9, the measurable suction is very, very difficult, you know, it's highly sensitive. So beyond 2000 kilopascal, detectable suction is beyond 2000 kilopascal. Osmotic technique is for less than 2000, 3000 kilopascal. This method is good for beyond 2000 kilopascal. Similarly, vapor equilibrium. Yeah, I do have, you know, here sensitivity is very high, right? So here 99.9, 98, all those things are here. So you can't measure. The variation is very less. Here variation is good. With temperature, it's not sensitive. So this is a WP4, and this was already mentioned because we discussed the change in the RH due to presence of salts. Because chemical potential of the water decreases with increase in the salts content. Therefore, based on that, we actually have salt solution placed here. Under the same vapors, the samples have been kept. So we are trying to equilibrate, right? So if the salt solution, if it is a water, then the soil get wet. If it is K2SO4 or something, and if this is a saturated condition in the beginning, then water content will decrease, right? We did with the compacted samples in this manner, right? We actually continuously, the vapors have been flown to the both sides of the samples, and this is how the compacted samples, the SWs have been established. There is a simple method also. I'm sure some of you who worked in unsaturated soil mechanics would have definitely used it, which is a filter paper method. Filter paper, just like the porous stone, which has kind of uniform pores, the SWCC of this particular filter paper is established. Whether it's a Wattman filter, that means it has particular size. For that, this is already established. How did they establish? Huh? They use vapor equilibrium, right? Pressure plate, amount of water droplets that come out is difficult to measure, right? So some of the methods which I described previously, you would use that to establish the SWs of the filter paper. Now you keep the filter paper either in contact or away from the soil to evaluate the suction. If it is in contact with the soil, you will evaluate metric suction. If it is away from the soil, you will evaluate total suction, because it comes in equilibrium with the vapors, right? Yeah. So this is the total suction measurement. So these are some of the methods which are commonly used, like negative column, tensiometer, range. But range is, that can vary. I just gave some numbers, general figures, but it can change depending on where you are located, elevation, right? And axis translation around 1500, because 15 bar AEV is used. If your air entry disk is of capacity only 2 bar, range is only 200 kilopascal. So osmotic, even we went beyond this. We use certain membranes with which we went up to 7000 kilopascal. Dew point potentiometer beyond 2000. So it also takes a lot of time, and you can't use compacted samples, correct? Because you need to place inside. The small samples you have to place, it is not possible with the compacted samples. So laboratory methods. These are all laboratory methods. Tensiometer could be field method. Vapor equilibrium, lab method, and non-contact and contact filter paper. Right? Any questions?
Yes.
One by one. Yes. Mike.
In the contact filter paper method, when do we terminate the test? Like this is sandwiched in between. So how do we know that there is no change? Is it that we just have to keep it for a long time?
Yeah, keep it for a very long time. And we need to sandwich between other, 2 more filter papers or something at least we keep, because otherwise soil particles will come in direct contact with the filter paper. They clog the filter paper, and there will not be any water exchange that may not take place. So therefore, generally we keep more number of filter papers. But problem is, when you are going for smaller and smaller water contents, how do you measure weight, right? So there are a lot of issues, of course. I never used filter paper, although this is very simple to use. Simple to use, but complex to analyze the readings, right? Yeah.
Yes, sir. One doubt has solved. The other is like, what is the significance of this axis translation term? Is it something with a stress tensor or something? But
The axis has been changed. We were actually thinking about UW, etc. Now they moved to UA. They started controlling UA, right? The axis of control point has changed. That's how they named the axis translation. Yeah. And the same method is used for hydraulic conductivity, which is called multi-step outflow technique. So same method. If I have slides, I'll show you. So this is these are the data on bentonite sample, which is starting from slurry state, right? When initially slurry state was kept, and we analyzed, and these are the readings we got when we merged with the VSC, right? This is with the VSC. Volumetric shrinkage curve, I showed different methods in the morning, I think, right? So we found that Claude method is the best method, and we got very good data for the bentonites. This is a powder bentonite. Initial state is at liquid limit nearly, right? This Gapak is my first student, Yagam Gapak. So yeah, hysteresis also we estimated. And some of the models, today it was discussed. I didn't discuss any of the SWCC models. I could not get a time to discuss. So that's why this extra class, you may think, So, so this is the Richard equation. Richard equation in original form, not even an original form, maybe, yes. So you will have theta and psi, both will be the dependent variables. So here, these two are what we are trying to evaluate. One is this one, other one is this one, right? This is one constitutive relationship, SWCC. This is another constitutive relationship, hydraulic conductivity function. I don't know whether to call constitutive or not, because constitutive generally between two state variables. Hydraulic conductivity, I don't think it's a state variable, therefore it may not be a constitutive but a relationship, variation or functional form of hydraulic conductivity. And this is a specific moisture capacity, the slope of SWCC itself. Okay, and you will interestingly get the k times, if you bring theta psi out, you will have theta by dou z, right? In that case it becomes k times dh. If I write in terms of dh, dh by d theta, this is dou theta by dou z. This particular thing has units of what? This is meter per second, this is meter. That is a diffusivity, meter square per second, okay, which has some significance. So I think Professor Claudia showed the Brooks-Corey method for hydraulic conductivity estimation, but actually this was given initially for SWCC, and same thing has been adopted for hydraulic conductivity function. So simple models are there, like this is a Van Junisten model. So essentially what we are trying to do, we have a lot of data, right? Experimentally we are measuring data, theta versus psi. We are trying to fit equations or empirical forms to predict continuous observations or continuous data. Because what happens, to solve this expression you require a continuous function, k of psi or psi of theta. In a continuous form you require. You can't use a discrete data here to solve this one. So you require predictions. So models are there. So like Van Junisten, Brooks-Corey, Fredlensing, these are some of the models we often use. Okay, I'll not go detail which is better, which is not better, etc. But there are models. There are a number of models, like as I said. On the other hand, for the hydraulic conductivity function, also you have some empirical models. In fact, you require more number of models for hydraulic conductivity function, because it is very difficult to estimate in the laboratory or in the field. Most of them are not accurate also. We may estimate and we get some data, but then it may be accurate or may not be accurate due to some limitations. These are some of the models. Some of them are empirical, some of them are macroscopic, like Brooks-Corey, where with some parameters which is related to pore size distribution they are trying to evaluate. They are macroscopic. Empirical are purely based on fitting the data. Right? There are some statistical models, like Hagen-Poiseuille or Childs and George, what she was mentioning. These things could be used to evaluate the hydraulic conductivity function from the SWCC data without even fitting using Van Junisten or something. So this could be used. In fact, my regular classes I solve this one, and in fact I think in NPTEL also it should be there. Okay. So Burden Moolam, here you require models. Like Jackson also is one of the models which is derived from Childs and George. And these two models you can integrate with Van Junisten to get analytical expressions for hydraulic conductivity function, right? So this is what we are doing. You have SWCC using retention models, water retention models, I mean to say SWCC models. We are getting a functional form. From there, using statistical models, we are predicting the hydraulic conductive function. We use in the modeling of infiltration or evaporation or whatever it is. Right? For evaporation, we might require drying data. We may require wetting data for infiltration. Right? I just want to mention, because today morning after the discussion, I thought I'll just quickly mention how the Richards equation has come. Although this is 19 and 11, I don't think there is a replacement to this, but there should be. But at least this is good for most of the soils. Even expansive soils are confined, there might be expected some changes, but it is good enough. What it contains is just like if you know the derivation of consolidation equation, there is a derivation, right? So which is derived after this, that is in 1920s, 23, 27 sometime by Terzaghi, consolidation equation. This is derived in 1911, 11. Exactly the same. There he plays with the state variables and then brings those u values, etc. For that he uses additional one constitutive relationship called sigma dash equal to E, sigma dash equal to function of E. That is one constitutive relationship to change the variables. Otherwise, if you don't change the variables, exactly the same. You have mass conservation equation, this is mass conservation equation. Right? After this Darcy's law, then you got the expression. That's it. That is your Richards equation. Fine? There is one old derivation for estimating the diffusivity. Diffusivity I just defined. K times dH by d theta. Slope of the SWCC. Right? This is by Bruce and Clute, 1956. Please remember the date. 1956, long back. Using the Boltzmann transformation, using the theta variable, so he converts psi also into theta, and then he does this. He gets the diffusivity. Now, if I have SWCC, which is psi of theta, if I can measure this, can I get K? Yes. So that is one possibility. I took a soil sample. This is our work. This is bentonite, right? Bentonite compacted at different densities, starting from 1.2 to even 1.8 gram per centimeter cube, dry density, and connected to reservoirs, water reservoirs. So water is flowing, you could see water is here, water is here. So there's a wetting front which is moving in the soil samples. Then what I do, I actually extract the soil samples. I push from the dry side, from this side. I actually slice it. If you think the water distribution is 1D, maybe it distributes because this is the column. If it is connected to water reservoir, you expect that the flow distribution is something like this or something like this. If that is so, if I cut here and here, there will be difference in the water distribution. If I see the core and periphery, almost the same. That means water distribution is going like this, right? I require the minute details to use my 1D model. SWCC was independently established, as I shown previously, Vepre equilibrium, osmotic methods, etc. And I got the parameters. So these are different dry densities, the VG parameters, alpha and n, FX parameters, Fredland and Shing, alpha, M, N, CR, which has 4 parameters. We evaluated. Even R square is also very good, right? What I get from here? Water content variation with respect to space and time. If I do multiple samples like this and connected to heads at different time periods, and I sacrifice the samples, I expect that the moisture movement within the soil sample at different time intervals and different depths, lengths also, distances also from the reservoir. So these are data what we got. What I can do, I can solve the Richards equation because I have the K function. Sorry, I don't have the K function, but I have SWCs. I can predict the K function using statistical methods like Moolam, Van Jenisten Moolam, Van Jenisten burden. These models are there. Similarly, Fredland, Xing, Huang or somebody, WXH Huang. These guys have given a different hydraulic conductive function. We have used all those statistical models to predict the hydraulic conductive function. We inputted the HCF and SWCC in the Richards equation. If we try to predict, look at the predictions. The data is here. The predictions are here. Right? Not this one, this one. Van Jenisten and this is Fredland. What does it mean? Either Richards equation is not fine for this, or K functions are not properly evaluated for using the statistical models, because SWC is measured. SWCC is measured, and then we have a measurement of flow, transient flow. What went wrong? Either Richards equation or K function, HCF. Right? Richards equation probably fine because volume change is not allowed. Here it's isochoric conditions. In the column, we don't allow the soil to expand. Okay? Something I missed. Yeah. We have these predictions based on determination of the diffusivity from the earlier method what I just showed you. The Clute. Bruce and Clute. Using this particular method, we evaluated the diffusivity because you require what? X by root T and theta. So based on that, I can evaluate diffusivity. I know the diffusivity. I know the SWCC, therefore dH by d theta is known. I can evaluate K. So that's why if I evaluate the K, our predictions are better. Right? And using the instantaneous profile method, there were publications already where they say that the hydraulic conductivity function started increasing beyond certain suction, which is not possible actually, but it was justified that there is a mineralogy change or something. Therefore, we evaluated the mineralogy also. Nothing happens here. There is no change in the mineralogy except the pore size changes are happening. Right? So this is there, published in Geotechnical Journal Environmental ESC. I think I thought of covering the last portion because there are methods to evaluate the hydraulic conductive function apart from multi-step outflow technique and other things. So any questions? At least got some names of the methods so that we'll understand when we go to field or laboratory. Yeah, let's move then. Thank you so much. So we are moving to the ground where we are going to measure the flow, transient flow data using double ring infiltrometer. So therefore today it will be off from now, and thank you so much. What is it? Taros. What is it? Don't tell me that. Suction measurement. Same issues. Same issues. So it takes very long time to establish the equilibrium. Papers are there. Published by Professor Tripathi et al. I guess in Indian Geotechnical Journal. and later on we have some works also. Yeah. So measuring range is quite high. Almost it goes to the several hundreds of MPAs, but then it takes very long time. Yeah. Thank you so much.